You've probably seen those videos, the ones that show just how unimaginably large some stars are. Stephenson 218, a red hypergiant sitting roughly 19,000 light-years away, is the largest known star in the universe. It's 2,150 times wider than our Sun and has a volume about 10 billion times greater, meaning you could fit 10 billion suns inside it. And when you think about giants like Betelgeuse, Antares, Aldebaran, and Arcturus, stars that blaze as some of the brightest points in our night sky, even they look tiny next to Stephenson 218. Yet even comparing our Sun to those giants is a stretch, because next to them, the Sun looks like a speck of dust, a completely insignificant little star lost in the cosmos. Now, these comparisons are technically accurate. Our Sun really is much, much smaller than those massive stars. And honestly, those dramatic size comparisons in popular science documentaries have probably triggered an existential crisis or two, or at least shaped the way you think about our place in the universe. But here's the real question. Is our Sun actually a small star? Today, we're going to take a deeper look at astronomy, not just a surface-level glance, and discover how your entire perspective on our place in the universe might be about to shift. The Hertzsprung Russell diagram, or simply the HR diagram, should be the first thing that comes to mind when you think about astronomy. It's an indispensable tool for understanding both the life cycles of stars and how they're classified. Think of it as the periodic table of astronomy. Just as the periodic table is fundamental to chemistry, the HR diagram is fundamental to astronomy. You simply cannot understand stars without it. The horizontal axis shows the surface temperatures of stars, while the vertical axis shows their luminosity. Luminosity and brightness aren't exactly the same thing, but for now, you can think of them as brightness. So, the hottest and most luminous stars sit in the upper left corner of the diagram, while the coolest and least luminous ones are in the lower right. The horizontal axis also tells us the spectral type of a star. M-type stars, for example, are located in the lower right. They're relatively cool and red. Proxima Centauri, the closest known star to us after the Sun, sits right there in that lower right region. So where does our Sun fall on this diagram? The Sun is a G-type yellow dwarf. It has a near-average temperature compared to other stars and near-average luminosity, which places it roughly in the middle of the HR diagram, with a surface temperature of about 5,772 Kelvin and an average size. The Sun is, by all these measures, an average star. And notice, even at this point, just by looking at the HR diagram, we can already see that the Sun is far from the insignificant speck those size comparison videos make it out to be. There are countless stars that are far dimmer, far smaller, and far shorter-lived than our Sun. We've already moved the Sun from small to average, but what comes next will surprise you even more. To truly understand whether the Sun is a small star, we need to ask the right question. As you move toward the lower right of the HR diagram, you find stars smaller than the Sun. Move toward the upper left and you find larger ones. That thick, band-like region running diagonally across the diagram is called the main sequence. Stars spend the vast majority of their lives here, in the main sequence phase, fusing hydrogen into helium. This is essentially the stable, healthy phase of a star's life. Our Sun is currently a main sequence star, and because stars spend most of their time in this phase, about 90% of all stars in the universe are main sequence stars. But looking at the diagram again, stars like Spica, Sirius, and Bellatrix, all much larger than the Sun, are also main sequence stars. So the real question we need to ask is, what fraction of main sequence stars does each type make up? I've mentioned in previous videos on this channel that a star's lifespan is directly tied to its mass. I'll say it again here because it's crucial. Mass is the single most important factor determining how long a star will live. The greater the mass, the stronger the gravitational pressure, and the faster the star burns through its fuel. So high-mass stars live short lives, while low-mass stars live long ones. In the world of stars, it's live fast, die young. This simple rule means that low-mass stars vastly outnumber high-mass ones in the universe. In our galaxy alone, approximately 70 to 80% of all stars are M-type red dwarfs. Massive, high-mass stars burn through their fuel quickly and die young, while red dwarfs burn slowly and steadily for extraordinarily long periods. Over time, this causes the red dwarf population in the universe to keep growing. As a result, M-type red dwarfs in the lower right of the HR diagram make up somewhere between 70 and 80% of all stars in both our galaxy and the observable universe. This means that comparing the Sun to supergiants and hypergiants isn't particularly meaningful. Those giants make up only a tiny fraction of all stars. The Stephenson 218s, UY Scutis, Betelgeuses, and Antares of the universe, the kinds of stars featured in those popular size comparison videos, account for at most 5 or 6% of all stars. So that star we thought was tiny and insignificant? Our Sun is actually larger than at least 70 to 80% of stars in our galaxy, and larger than roughly 80% of all stars in the observable universe. And not just in size, but in mass and luminosity too. And we're not talking about a marginal difference. Many of those red dwarfs are so small, they're comparable in size to gas giants like Jupiter. Looked at from this angle, the Sun is actually a massive, brilliantly luminous, high-mass star compared to the vast majority of stars in the universe. Larger, brighter, and more massive than over 80% of everything out there. And since a star's lifespan is directly tied to its mass, the extraordinary brevity of those supergiant stars, compared to the red dwarfs that numerically dominate the universe, is almost always left out of the conversation. Even the most massive red dwarfs have lifespans measured in tens of billions of years. Keep in mind the universe itself is only 13.8 billion years old. That means these stars have lifespans at least as long as the age of the universe. Lower mass red dwarfs can live for trillions of years. So here's the real irony. Those dim, low-mass red dwarfs we so easily overlook. They will outlive the Sun and every other star we know. Long after the Sun and all other stars have burned out and gone dark, red dwarfs will still be burning. They will be the last stars standing in the universe. So, to sum it all up, not only is our Sun far from being the small, insignificant star it's made out to be, but even calling it average is arguably an understatement. What do you think? Are we doing our Sun a disservice by calling it a small star? Let me know in the comments. Take care of yourselves, and I'll see you in the next video.